to have sort of a correctly balanced equation when you're all said and done. The two main things that we talked about were all the coefficients do need to be whole numbers. We talked about you can use a fraction to balance, but you do have to get rid of the fraction to sort of have a properly balanced equation. The other thing is they do need to be the simplest set of whole numbers when you balance an equation. The goal, obviously, of balanced equation is the idea of conservation of everything, pretty much. So, we start with like 5 carbons, we end with 5 carbons on the other side. We also talked about, or really started talking about, I think, ways to classify reactions. And we were talking really about sort of a big umbrella of classifications, which is known as double displacement reactions. And double displacement reactions basically have the general formula of AB plus CD. And what makes each of these things what they are is they are ionic compounds, which means we have a positive and negative guy. And always in a double displacement reaction, we do get our 2 positive guys basically to switch partners. And we end up making 2 new ionic compounds on the product side in this particular case. Now, as this is sort of the kind of big umbrella for which you can also classify several different types of double displacement reactions that take place. And a couple that we talked about, I believe, or we're sort of in the middle of talking about, were ones that are referred to as precipitation reactions. So a precipitation reaction really is nothing more than a double displacement reaction. What makes it a precipitation reaction is that on the product side, we do form something that basically is a solid. And we'll talk about, how you know which one's a solid. So basically a precipitation reaction involves a solid being formed on the product side. It ultimately is still a double displacement reaction, but again, sometimes classified as a precipitation reaction. In addition, another very common sort of double displacement reaction is an acid-base reaction or an acid-base neutralization reaction. And what we end up doing usually, as we will talk about in these type of reactions, is essentially form water. It's kind of a common thing that's formed as a result of that. Again, ultimately what's happening is our double displacement reaction. But it can also be classified sometimes as an acid-base reaction. We also, by looking at these type of reactions, last time talked about kind of 3 different types of chemical equations that we often associate with these type of reactions. And one is what we associate with every type of reaction, which is really just the molecular equation. So if we take something, I think this was the one we looked at the end there last time, some lead to nitrate plus some sodium iodide makes our lead to iodide, which is a solid, and our 2 sodium nitrates here. Now, a couple of things about this reaction, as we talked about, this is obviously what is referred to as the molecular equation. And it is typically the equation or the reaction or the way we sort of express the reaction, where we use obviously all the formulas and of everybody correctly written. It is also really a double displacement reaction. Again, this lead is positive, this nitrate's negative, sodium is positive, iodide is negative. So what happens is basically what we talked about, the 2 positive guys will switch partners. And that means on the product side, the lead and the iodide will come together to make our lead to iodide. And the other positive guy will then hook up with our other negative guy, and that means that our sodium will then go and hook up basically with our nitrate here, and that's how we get to our basically sodium nitrate in this particular case. So this reaction can definitely be classified as a double displacement reaction. It could also be classified as a precipitation reaction, because as you can see, this lead to iodide is a solid. So some type of solid was formed as a result of that. So a lot of times when we're dealing with solutions and sort of our aqueous solutions, sort of mixing solutions together, we could write our molecular equation. We could also write another equation that really describes what is happening basically when we toss this whole thing into a beaker, into a test tube. And this is what is sometimes referred to as a total ionic equation, or sometimes referred to as the complete ionic equation. And basically what we do is we go through our molecular equation, and everything that is aqueous, pretty much that's a strong electrolyte. So that's something else we talked about last time. A strong electrolyte is something that 100% breaks apart into ions in solution. And as long as it's not a weak electrolyte, which we also talked about, which mainly stays together, but if it's a strong electrolyte, we pretty much will break it apart into its ions. So something like lead 2 nitrate, really when it's in the beaker, in the test tube, it's not going to stay together. It's going to 100% break apart into lead 2 ions that are floating around in that solution. We will also get a couple of nitrate ions floating around that solution. So here, when we go from our molecular equation to our total ionic equation, the little 2 actually comes to the front. The sodium iodide will also break apart, and we'll get a couple of sodiums. So you can see we also distribute the 2 that's in front to both of these guys, and we will get 2 iodides as well. Now, when we do these sort of total ionic equations, complete ionic equations, we want to keep together anything that's a solid, a liquid, a gas, or a weak electrolyte. So anything that's a solid, liquid, gas, or weak electrolyte stays together. So in the case of our lead 2 iodide, we would keep it together just like it is up there because it's a solid. Our sodium nitrate will also break apart. Again, we're going to distribute that 2 to both of those guys, and that will give us 2 sodium ions and 2 nitrate ions. And this is really the equation that describes what is going on kind of in that test tube, in that beaker. We have all these ions floating around. We got some of the solid that's being made along the way. When we write our total ionic equation, we should always be able to look on the left-hand side of the arrow and the right-hand side of the arrow, and we should be able to find ions that look exactly the same. So if we look, we see nitrate here. There's 2 of them, and there's 2 nitrates over here. They're exactly the same. We see 2 sodiums over here, and we see 2 sodiums over here as well. They are exactly the same as well. These ions that you find on opposite sides of the arrow, which are exactly the same, these are guys like we talked about last time, which are referred to as spectator ions. So these are our spectator ions. Now, spectator ions, as we talked about last time, are essentially what the name implies. If you are a spectator, you're essentially watching what's going on. You're not really participating in what's going on. You're just sort of watching. And what we typically do is we cross out those spectator ions on each side. Now, your spectator ions should probably always cancel out completely. So if you get to this point and you're crossing out your spectator ions and you got different numbers on the left-hand side and the right-hand side, that probably means something's not balanced correctly. So they should probably always cancel out completely. And what we're left with is the third type of reaction we kind of talked about there at the end last time, and that would be our lead and our iodide forming our PbI2 solid. And this is what is referred to as the net ionic equation. And what is the net ionic equation? Well, the net ionic equation essentially gets right to the heart of the matter and tells you exactly what is happening in this reaction. So although we're dumping in some lead to nitrate, we're dumping in some sodium iodide, what is really happening in this reaction is the lead ions are coming together with the iodide ions, and they're making this solid. And the solid is like that yellow solid I think we saw last time. And the net ionic equation, like I said, really is the equation that explains to us or shows the person the underlying overall sort of reaction that is taking place. Any questions on that stuff there we talked about last time? Now, in addition, I think we also talked about this, but just make sure, and it's sort of the basis of, what we're talking about in these different types of reactions. There's really sort of three sort of driving forces for a reaction to take place, a chemical reaction to take place. And those three things typically are the formation of a solid, like what we got going on here in a precipitation reaction, the formation of water, like what we have in the acid-base reaction that we talked about or will talk about again, and really an electron transfer. So these are like kind of three really purposes or sort of why reactions take place. Is either we want to make a solid, we want to make water, or we want to transfer some electrons. And these are all, again, like I said, sort of the reasons behind certain reactions as to why they take place. So let's take a look at another one here. Again, these are sort of the steps to get us to these net ionic equations. So for example, if we look at this one, we want to write the net ionic equation for the reaction of silver nitrate and sodium chloride. So the first thing you would want to do if you were going to write this reaction is you want to start with the overall equation, and you want to make sure that you get the overall equation balanced. So it tells us that we are reacting silver nitrate, which is AgNO3. I'm assuming you know that since there's a nomenclature exam happening very shortly. So that is silver nitrate plus some sodium chloride, which is NaCl. And we want to predict what's going to happen on the product side here. And in this case, if you're not sure what's going to happen, you want to analyze what you're starting with. You should be able to recognize that's a positive guy, that's a negative guy, that's a positive guy, and that's a negative guy. So that should really tell you this is a double displacement reaction. It's kind of your trademark double displacement move. That means that the positive silver should end up with the negative chloride over here in this area here on our product side. Since I got the color, I'll color it in first. So when we put these together, and as we talked about when we talked about balancing equations, you want to put these guys together just like you would do in naming. So silver has a +1 charge, chloride has a -1 charge, which means when they come together, they will make silver chloride, AgCl. Remember, not interested in balancing at this point. We just want to make sure we get down the right formulas first, and then we could go balance. That means that the sodium, which is the other positive guy, will hook up with the nitrate, which is the other negative guy there in a situation over here. We'll pre-color it in here. And again, when we put those two things together, we just want to make sure we put it together correctly. Sodium's +1, nitrate is -1, and that will get us NaNO3. Now that I have all the correct formulas down, I just want to make sure it's balanced. And if you look at it, you do have a balanced equation. We got one silver on each side, a chloride on each side, some sodiums on each side, and one nitrate on each side. So it is actually balanced. Now, what we would then do, obviously, this would be our molecular equation. The next thing we would want to do is our total ionic. So again, we would want to break up everything that is aqueous. So our silver nitrate would break apart into a silver ion plus a nitrate ion. Our sodium chloride would break apart into a sodium ion plus our chloride ion. Again, anything that is a solid, a gas, a liquid, or a weak electrolyte does not break apart. So silver chloride, which is a solid, would stay together. And our sodium and our nitrate would break apart here. Again, in our total ionic equation, that is where we should be able to identify our spectator ions. So again, if we look at this, I see nitrate on the left, I see nitrate on the right, I see sodium on the left, looking exactly like the sodium on the right. And again, those guys there would be our spectator ions here. So we're going to, again, get rid of our spectator ions as they are really not participating in, excuse me, what is happening. And that will leave us our net ionic equation, which is pretty much what's left over. And that means really what is happening when you mix those two things is the silver ion from the silver nitrate will go find the chloride ion from the sodium chloride. And those two guys, when they come together, will make a solid or a precipitate known as silver chloride. Any questions on any of those steps there? Now, a question that some people might have is, how do you know what's going to be solid, what's going to be aqueous? And that's a good question. So let's talk about how you actually can predict, what is going to make a solid, perhaps what might not make a solid. And what helps us do that is what's known as solubility and solubility rules. So solubility rules helps us determine whether or not when we put two things together, like in an ionic compound, will that lead to a solid being formed or will that lead to no solid being formed? So let's talk a little bit about that there. Solubility is, as I mentioned, the maximum amount of solute that will dissolve in a given amount of solvent at a temperature. Solubility is really based on temperature. So depending on the temperature, you can get more to dissolve, you can get less to dissolve. When we do get everything to sort of dissolve together and mix together, that's really what a solution is, right? When we talk about a solution. And that is really, what it gets that aqueous symbol that we put there. Remember, as we talked about, I think before, the difference between aqueous and a liquid. A liquid is really just one thing by itself, not mixed with anything else. And aqueous is really a solution, which by definition means something like a homogeneous mixture, which basically means that you mix something together. Usually you mix a solute with the solvent. So when we talk about a solution, there's really two parts. There's the solute, which is the smaller part of the solution. And there's the solvent, which is the larger part of the solution. So for example, if we had a solution of sodium chloride, right? Salt water, basically. The smaller part of that solution would actually be the sodium chloride, would be the solute, dissolved in something like water. And that would get the aqueous symbol when they come together. Water would be a pure liquid by itself, but once we mix in some of that sodium chloride to it, it will dissolve and make that solution. Now, we could use solubility rules, which we'll see here in just a second, to help us determine, again, whether or not we expect a solid to form or not. If something based on solubility rules is deemed to be soluble, what that means is pretty much it will mix together, you will not get any solid, and it will get the aqueous symbol next to it. If you look at the solubility rules and it says this combination is insoluble, that means that when you mix those guys together, you would expect some type of solid to form, and those guys would get the solid symbol next to it, or a precipitate to form. Any questions on that there? So let's take a look at some of these solubility rules. These are guys that are typically soluble in water. So these are guys that typically means they are soluble, which typically means they will be aqueous. Now, if we look at something like lithium, sodium, potassium, or ammonium, basically group 1 is these guys, right? These are group 1 over here on the periodic table. Group 1 on the periodic table and ammonium. There are no exceptions, which means as soon as you see one of those sort of elements in a formula, lithium, sodium, potassium, anybody from group 1, or you see ammonium in the actual formula, you pretty much don't need to go any further. That guy should get the aqueous symbol. It should be soluble. In addition, things that have nitrate in the formula are acetate, also going to be soluble no matter what. As you can see over here, there are no exceptions. And again, as soon as you see something that has nitrate in the formula, you know automatically that it's going to be soluble. Chlorides, bromides, iodides are also going to be soluble, but the difference is we have some exceptions. So what does this mean? Well, if we look at the table, if somebody is on the left-hand side of the table, that means that they are aqueous. But if there is an exception, so if you have, say, silver with bromide, instead of being soluble, the exception would be the opposite, and it would be insoluble and typically get a solid there written, basically. So if you have any one of these three guys, silver, mercury 1, that is, lead 2, it will become insoluble and would get the solid symbol. Sulfates, again, are typically soluble. The exceptions would be silver, calcium, strontium, barium, and lead. If you have any of these guys, it would be opposite of that, which means they would be insoluble and you would get a solid. So using these sort of solubility rules will help us determine whether or not, when we look at something, would we expect it to, again, make that solid or make something that is insoluble, which would be solid, or something that is soluble, which would be aqueous. Any questions on those rules there? Now, there are some rules that apply to things that are typically insoluble. So when we talk about these guys on the left here are typically insoluble, which means they typically will get the solid symbol unless they have an exception with somebody on the right-hand side. And if they're on the right-hand side, they will then become aqueous or soluble. So hydroxides are typically insoluble, but there are some exceptions, and these exceptions are pretty much what we saw on the previous slide. That's our group 1 and ammonium. And again, if you have any of those guys like sodium hydroxide, they go from being insoluble to soluble and would get the aqueous symbol. Also, barium, strontium, calcium are what are referred to as being slightly soluble. Sometimes on tables, they'll actually list that as SS, slightly soluble. And most of the time, slightly soluble leans a little bit towards being insoluble. slightly soluble means that some of it will dissolve, but a lot of it will not dissolve. So usually in terms of slightly soluble, people lean a little bit more towards it being insoluble in that case. Things that are sulfides or solids makes a lot of really smelly solids. But again, our same sort of exception, our kind of group 1 here, and NH4 plus, along with barium, strontium, calcium, some of our group 2. Again, if it's these guys involved, it will go from being insoluble to soluble in this case. And lastly here, carbonates and phosphates are typically insoluble. Again, with our group 1 exception happening here, would turn them aqueous or soluble. So these rules, again, really do help us determine, like in those couple of equations like we looked at before, where we took some silver nitrate plus some sodium chloride and made some silver chloride and some sodium nitrate. So again, if we weren't sure what was going on in terms of these sort of states, we would use our solubility rules and go, all right, I may not see silver on the list, but I definitely see nitrate on the list. And when I see nitrate on the list, it is soluble. There's no exceptions. So that automatically tells us as soon as we see that nitrate that this guy is going to be aqueous. I go to sodium, which is on the list. It is group 1. There's absolutely no exceptions, which automatically tells me I don't even need to go any further. That is going to be aqueous. I may not see silver on the left, but I do see chloride on the left. Chloride is right here. Chloride is soluble in everything, but there are some exceptions. And one of the exceptions is silver. And because this is silver with chloride, instead of it being soluble like normal, it will now become insoluble. And that's how we know the silver chloride is a solid. I look right here at sodium. That is pretty much as far as I need to go. There is no exceptions. I could even look at nitrate if I'm not convinced at that point. And again, nitrate, no exceptions. They both tell us that this guy would be aqueous. Questions on sort of using that rules there. And again, if we look at the other reaction that we saw there, which was lead to nitrate plus our potassium iodide going to our lead 2 iodide plus our potassium nitrate. Again, using the same approach, although we may not see lead, I do see nitrate. Nitrate is soluble in everything, no exceptions, which means I'm good to go with the aqueous. I take a look here at potassium, which is group 1. That means that's as far as I need to go. I don't need to go any further, and that will tell me it's aqueous. Again, may not see lead on the left, but we do see iodide on the left, which is right here. But we do see lead on the right as one of the exceptions. So instead of iodide normally being soluble, this would be insoluble in a solid. And at this point, you could look at the potassium, which is soluble in everything. You could even look at the nitrate, which is soluble in everything. And that would get us there. Question on how to use solubility rules. All right, let's take a look at these few here. So using our rules here, let us see what we should be looking at in terms of determining whether or not these guys are soluble. Well, looking at potassium nitrate, it really is the potassium part is all you need to look at. That is group 1, which means it's soluble in everything. There's no exceptions, which means this guy should be soluble and should really get the aqueous symbol next to it. Here, again, if you look at that table, may not see silver on the left. We'll see bromide on the left. Bromide is normally aqueous, but because in this case it is actually hooked up to silver, that's an exception, which will then turn it from aqueous into a solid, and we would expect this guy to become insoluble and a solid to occur, and this guy would again be insoluble and really receive the solid notation there. Looking at calcium chloride, again, looking at calcium, may not see it on the left, but we'll see chloride on the left. Chloride is soluble in everybody except, as we've been talking about, silver, lead, and mercury. And in this case, that is none of the exceptions. So that would mean that this guy would be aqueous because of that. Again, because chloride is not attached to silver, lead, or mercury. So because it's not an exception, it should be soluble. Lead to nitrate, as we talked about earlier, that's pretty much all we need to look at. We see nitrate. We're pretty much done at that point. Again, nitrate is soluble in everything. Don't have to look any further. And lastly, we have sulfate here, which is where we want to look at. Lead 2 sulfate is insoluble. Most sulfates are soluble, but lead is an exception to that. And again, if we look back at our table there, it was sulfate. This again is the guy that's soluble in everything. And this is the one of the exceptions, which would turn it to become insoluble. Any questions on sort of how to use that table correctly? All right, so why don't we take a look at one here, give you a chance. Let us do the what we want to do here. Let's do this one here. Let's do all three of those equations just to make sure. So why don't you write the molecular formula that's balanced equation? Why don't you do the total ionic equation for this guy? And why don't you do the net ionic equation, balanced and states? So we're doing a combination here of potassium carbonate plus some nickel 2 chloride. And again, you need to predict what it forms, balance it, write the total ionic equation and net ionic equation. So why don't you take a few minutes? I'll let you figure out the formulas. It'll be good warm up for later, I suppose. Okay, let's take a look and kind of see how you're doing. So let's start with, obviously, before we could get anywhere, we want the molecular equation, which means we need the correct formulas. So here we have potassium carbonate. Potassium is K plus, carbonate is -2. That means the correct formula would be K2CO3. Nickel 2 means nickel has a Roman numeral 2, but it has a positive charge of 2. And chloride, I think is what I scribbled there, is -1. That means that we would then be plusing it with nickel chloride, looks something like that. You should hopefully recognize this as a positive negative guy, positive negative guy. So as we've been talking about, our two positive guys are really going to switch places there. Important in this case is we want to make sure that we actually get the correct formulas first and not worry about balancing. So what do I mean by that? I mean, when I look at potassium carbonate, the two basic things that make it up is a potassium ion and a carbonate ion. The nickel 2 chloride, the two basic things that make this guy up is a nickel with a +2 charge and a chloride with a -1 charge. I am not concerned at this point about these 2s, because if I am, I'm going to end up with the wrong formula. So I want to make sure I get the right formula first and then balance it so I don't end up messing up. That means my potassium and my chloride will come together, and it makes the proper formula for potassium chloride, which is KCl. Not my favorite one that everybody likes to write, K2Cl2, because they see the 2s on the left-hand side. So again, we're going to take care of those 2s later on by balancing the equation. That also means my nickel and my carbonate here come together. Again, the basic units is +2 and -2, which means I essentially just need one of each of those guys there. Any questions on sort of the proper way there to take care of that? Now, once we have the correct formulas on the right-hand side, now we could go and balance it. And it looks like perhaps we just need a 2 in front of the KCl. That gives us 2 Ks on each side, 2 Cls on each side, a nickel and a carbonate. So we are now balanced. Any questions on that part of it? Now that we have the molecular equation with the correct formulas, with them balanced correctly, we can now go to our solubility rules to help us determine what is aqueous, what is solid. Again, looking at my first one, as soon as I see my potassium there, that is group number 1, which means there's no exceptions. That is always going to be aqueous. When I look at the next guy, I could look at the chloride, and that is always aqueous, except when it is, or soluble, except when it is with silver, lead, or mercury. And that is not the case here. So this guy as well would get the aqueous symbol. Coming to my other side, I could take my pick here, but I could pretty much stop right there by looking at the potassium. Potassium, just like on the other side, soluble and everything, going to be aqueous. I could also look at the chloride if I want, soluble in everything except for silver, lead, and mercury, which is not the case here. When I come over to my nickel 2 carbonate, carbonates are insoluble except for a few group 1s, which in this case it is not group 1. And that means that this guy is going to be insoluble and the solid here. Any questions on how I got to my states? This now would represent the molecular equation with all the states and everything properly balanced. We now can proceed to break this guy apart into our total ionic equation, our complete ionic equation. Remember, we're going to break apart everything that is not a weak electrolyte, that is not a solid, a gas, or a liquid. That means my potassium carbonate will break apart into 2 potassiums. The 2 comes to the front, and 1 carbonate ion. The nickel 2 chloride will also break apart into a nickel ion with a +2 charge. The 2 chlorides will make the 2 come to the front. This guy coming to the front here of the chloride. Coming on our other side, the 2 here will distribute to each of these guys, and that will give me 2 potassiums plus 2 chlorides. And here we have a solid which will stay together. That is nickel carbonate, which is our solid. That would represent our balanced total ionic equation. Any questions on that one there? Again, at this point, we want to look on both sides and find some ions that look the same. So I see a potassium there, see a potassium there. I also see a chloride, a couple chlorides over here. See a couple chlorides over here as well. That means that what we are left with is our spectator ions here that we're going to cancel. So those would obviously be our spectator ions. And now we could get to our net ionic equation, which is pretty much what is left over. So basically what happens in this reaction is the nickel ion goes and finds some carbonate ion, and it makes a solid of nickel 2 carbonate over here. And this is our net ionic equation. Any questions on that one there? A couple of important things to remember when you're writing these type of equations is total ionic equation and a net ionic equation. What does that mean? It means you should have ions. So when you write these things, you need to make sure you include the charges. So if you're writing a total ionic or complete ionic equation or a net ionic equation, it does need to have ions and charges. The molecular equation obviously doesn't need it because everything should be balanced, but total ionic and net ionic equations should. Any questions on any of those sort of steps there? Okay. What we're going to do is we will lay it up